record button, and we are recording. Good. So we've talked about circuits quite a bit, and I'm just going to redraw a small circuit. I think that's bright enough. Okay. So we have used these kind of circuit diagrams. And our simplest circuit looks something like this, where we have some kind of voltage source or power source, and this could be a battery or it could be a power supply, something that is provided either by the power company or by your physics teacher, where you can plug something into that. So this could also be kind of like a Steckdose, a wall plug that you plug something into. And this resistor is some kind of device that uses up power provided by the power supply. Okay, and then there's a current flowing in here. This is so far just review. Those are the three letters. And a certain amount of current flows into the resistor here, and out here comes a current out. Let's call this current 1, and let's call this current 2. What's true of current 2 compared to current 1? This is a question for you guys, and I'll call on somebody. I'll call on Lauren.
Can you ask the question again?
Sure. We have a power supply that's creating a current that flows through the resistor. We'll call that current I1. And then on the other end of the resistor, it could be a light bulb, a current comes out of that light bulb, and that's current I2. What can you tell me about currents I1 and I2? Are they the same? Are they different?
I think they have the same current throughout this whole resistor. I mean, throughout the whole what's it called? Circuit.
Okay, and if I asked you to justify, Lauren, why that's true, how would you justify that and explain that to somebody? Why is that true that the current's the same all the way through?
Wait, I need to look real quick.
Too tired.
Because if we look at Ohm's law,
okay,
I think the voltage divided by the resistance gets us the current.
That's true. Voltage divided by resistance is the current, but I'm not sure that clearly tells us right now that the current is the same. Let me ask you this. If you thought about this like a ski resort, what is the current? What is, in the analogy, what role is the current in our ski resort analogy? What aspect of, yeah.
The current is the, I think it's the, no, it's not. It's the people, sorry.
It's the people, that's right. So if we have like a little, I only have a little room over here, I think it's gonna be enough. Right? So we have our ski resort and our ski lift moves a certain number of people to the top, and then those people ski down.
I remember now.
Yeah, and they ski down. And another way of thinking about this is saying, okay, well, that power supply is kind of like the ski lift. That V is not showing up for some reason. This is a V down here. I'm not sure why that's not working out. I'm going to write it below it. We can make it bigger. This is, there we go. That's the power supply. And we have a certain amount of skiers that are dropped off at the top. And then the skiers ski down the slope, and then they start the process over. And they keep kind of looping through. And the skiers, in the analogy, of course, are neither created nor destroyed by the ski resort. Makes sense.
They are forever lasting.
They are. They hopefully, if you showed up at the ski hill with 50 people and you're all skiing here, then if nobody goes to lunch, it's still 50 people. It's not like, oh, you know, 3 people evaporated or something. That will be bad. Okay. In the same way, the charges that are flowing which is current, current is the rate of flow of charge, is also constant because a circuit does not create or destroy charges. Charges flow through it, but they are not created or destroyed by the circuit. Okay? That was just a quick review to make sure you guys understood that. And don't feel bad, Lauren, you had it half right. The explanation was a little lacking, but that's okay. I asked the question because I suspect that this is still not 100% clear, and that's okay. We're learning the thing, learning how this works. So here we go. We've got the current flowing. Good. And now we've got a question here. Of course, we call this thing, right? We gave that a name. We said a power supply, okay? Which makes sense. It supplies power because we use power for different things, to charge your phone, for example, which is, of course, something that's near and dear to your heart. So you have you call it a charger, okay? It's really a power supply that's supplying power for your battery on your phone to be recharged at a certain rate. Okay, and today we want to take some time to talk about power supply. And to do that, we'll do an example circuit. We've done this before. So we're going to say, okay, let's say our power supply has a voltage of 12 volts. Okay, and let's say our resistor over here is 3 ohms. Okay, so just kind of as a warm up a little bit, we've got a 12-volt power supply that's got a voltage of 12 volts, and we've got a 3-ohm resistor over here. How much current flows through the circuit if we have 12 volts applied to a 3-ohm resistor? Straight up circuit. And I'll call on somebody in just a second. So I'm giving you a minute to work on it. Just as a reminder as to the kind of laws that we have, this is Ohm's law. And normally we write it like this, but we can also rewrite it as a Idiotendreieck, right? Like this. There we go. Okay, good. So that's Ohm's law, and let's ask Isaiah to apply Ohm's law, hopefully, to find the current. Isaiah, how much current is flowing in this circuit that has 12 volts applied to a 3-ohm resistor?
4.
4, good. And what's the unit on that? Do you know the unit?
For A.
A is good, that's right. So this is 12 volts divided by 3 ohms, and of course that is 4, and the unit is amperes or amps. Okay.
Yeah.
So we found out that 4 amps are flowing. There we go. Cool. Great. Now we have said the voltage, it's 12 volts. We've said the current, it's 4 amps. We've said the resistance, it's 3 ohms. But we really haven't talked here about how much power there is. Okay. Now, the thing that's consuming the power, that's the resistor. The thing that's supplying the power, that's the power supply, duh, okay? So, but how much is that, okay? Now, a reminder about power. We did actually do a lab where we measured your power, okay? And what did we do to figure out how much power you guys were able to provide, supply?
Wait, who are you calling?
What's that?
Who should talk for this?
Oh, I'm sorry. I will call on Inessa.
What was it, the one where we had to run up the stairs?
We did have to run up the stairs, exactly. We ran up the stairs to measure how much power you guys had. And how did we express, what unit did we use to express how much power you were able to supply? And I'll ask Liam for that.
Use Pferdstock or horsepower. I can't
Okay,
say
so we have
which one.
Pferdestärke, correct? PS or in English, horsepower. Okay, that's correct. Okay, so we had a horsepower. We talked about that. So power, we talked about a horsepower. And we said that a horsepower is actually a multiple of the standard unit of power. What is the standard unit of power? And let's see if maybe Cassidy knows that.
Is it watt, I think?
It is watt, correct. So this is 700 and I think 46 watts. Yeah, and we're doing all this in English, but this makes a fantastic teacher/dad joke where you can say, was ist die Einheit von Leistung? Weiß ich nicht. Ja, nee, doch, was ist ja? Get it? No,
Mhm.
it's a terrible joke. Yeah, that's funny. It's really good, right?
Mr.
Yeah.
Blessman is so funny.
Yeah,
Everybody
that's good, right?
watching.
That's a good joke. Yeah, yeah. See, teacher jokes are better when they're worse. Is that right? I think that's true,
Yeah.
isn't it? Yeah.
That
good.
is completely true.
I mean, if they're actually funny, you're like, oh, cringe. I'm actually amused. This is terrible. So yeah, so you're welcome. Okay, so a watt is the unit of power. Okay, so a watt, kind of writing not too big because I want to make sure I get this on the screen as I have it right now because I like what we have here. So a watt is how much power is delivered. It's the rate of energy delivery. Okay, and the way we did this was we figured out how much energy you gave your body by lifting it up the stairs, right? And we did that by knowing your mass, gravitational acceleration, g, and the height you lifted, mgh, to find force times distance, which is how much work you've done. And that's measured in what unit? The energy that you get in that process. What's the energy unit? Anybody remember? And I'll call on somebody. Let's see if Mr. Feldmarsh knows. What's the energy unit?
I can imagine it'd be something like joules, maybe?
It is joules, indeed. So it's joules, correct? Okay. So if the unit of watt is the rate of delivery of energy, then it should be joules per time. And what's the standard unit of time, Matthias? Let's call on Matthias for that. How do we measure time as a standard unit? If you're not sure, Matthias, tell us a unit of time. How do we measure time in everyday life? And then we'll kind of work our way either up or down towards the correct unit.
Is he here?
Yeah, he is here. I think he's here. At least I
don't
saw
see
he's,
him.
yeah, Martina is his mom. So I think,
Oh,
or his
okay.
sister, actually. Sorry, not his mom, his sister. So I think that's him. Matthias, are you here? Can you just say hi?
You're muted, by the way.
I'm muted?
No, I mean Matthias, if he doesn't
Oh, but
know.
he was on just a second ago. I saw him click on and then say hi.
He texted in the chat saying that the Wi-Fi isn't good or
Oh,
something.
okay, good. All right, well, not good, but bad. But let's just move on then. And then let's ask, I think I'm through everybody except for Isaac. Isaac, what's the standard unit of time?
I guess hours? I'm not sure.
Hours
Minutes?
is a good guess, but not correct. Oh shit, I called
Never
you twice,
call on
didn't
me.
Yeah, Isaac just did it, I think.
I? Okay, I
I'm
just
pretty
called on
sure
you
he was
twice.
like the last person to do it.
Yeah, it was.
I called on Isaac twice. Sorry about that. That's my fault. Okay, so never mind. So it's not, indeed, it's not. Is Theo not here? Theo's not here. I just realized that. Okay, so
Nope.
he can watch the video later. Okay, anyway, the standard unit of time is not hours. It's very much shorter. It's a second. Good. So it's actually seconds. Okay, so we can actually write that out like that, or we can write a watt is equal to a joule per second.
Can you move the screen down for like
Yep.
just a little bit?
There we
Thanks.
go. Good. Okay, cool. Now we don't really have any statements about watt yet, so I want to remind you guys what the other things mean that we have, okay? So current is measured as amperes, right? Now, just a quick reminder, an ampere is a measure of the rate of flow of charge. Kind of like power is the rate of flow of energy, joules per second. Amperes is a rate of flow of charge, how much charge per time is flowing through our circuit. We said it's 4 amperes, okay? But we can actually express that more clearly by saying, okay, well, it's charge flowing, right? And what's the standard unit of charge? Are you guys aware of that?
No. I don't
Okay.
think.
I don't know, but I have an idea.
Okay, say your idea.
Volts?
Nope, it's a
Is
coulomb.
it coulombs? Oh,
It is a coulomb. So an ampere is
Never
a
heard someone
coulombs
use
per
a
second.
coulomb.
So when we have 4 amperes, what we actually have is 4 coulombs per second. Okay, that's a lot of charge flowing. Just as a comparison, the charge of a proton. So are you on my screen? I'm not on screen. That's terrible. So I'll write that here, just for comparison purposes. A proton has 1.6 times 10 to the 19 coulombs. It's a really small charge. So having 4 coulombs flowing through per second is quite a bit. Okay, so good. So we now know what that means, and we would like to get to this. We'd like to know how many joules per second they are, but so far we only know how many coulombs per second are flowing, 4 coulombs per second. Well, the connecting aspect here is, obviously, and Liam just mentioned it, he said, is it the volts? Something has to do with the volts. So we earlier on, I think, I don't remember if we did, but we should have at that point, but everything is blending a little bit due to Corona time. We should have done a similar thing for a volt and said, okay, well, what is a volt? What is a volt? What does that mean? 12 volts. What does that mean? Do you guys have any idea? If you don't, it's okay. Okay, I'm going to say you don't know. That's okay. It means that that's the amount of energy per charge. And specifically, it means how many joules does each coulomb of charge have? So if our circuit has 12 volts available for the charges that then flow over here, that means that each coulomb of charge has 12 joules of energy. Okay, so an outlet in Germany has 240 volts. That means that every coulomb of charge that flows out of that outlet has 240 joules. In America, it'd only be 120 joules. If you have a little flashlight battery, be 1.5 volts, be 1.5 joules per coulomb. Okay? Make sense so far? Now we're going to take this and look at these 3 things and say, we have how many coulombs per second are flowing, and we know that each, we know how many joules per coulomb we have. We'd like to know how many joules per second there are. So in our example, coming back up here, we know now that because it's 12 volts, there are 12 joules per coulomb. And we know there are 4 coulombs per second flowing through our circuit. Well, how much power is being delivered if we're delivering 4 coulombs per second and each coulomb has 12 joules of energy? How much power is being delivered to our resistor in that case if we deliver 4 coulombs per second and each coulomb has 12 joules? Oh, Lillian, I haven't called on Lillian. Lillian, I'm sure excited about having been called on now. How are you thinking?
I need some time. This is kind of confusing.
It is a little bit confusing. Okay, sorry. And we're a little tight on the end, so sorry about that. So the idea is, and I'll just kind of explain it at this point because we're out of time. I don't want to keep you necessarily much longer, and we'll get back to this. But the idea is if we're delivering 4 buckets, right? Which is kind of like this, and each bucket holds 12 liters. 4 buckets per second, each bucket has 12 liters. 4 buckets per second, 12 liters per bucket. Then each bucket brings 12 liters. We have 4 buckets. The total amount we're bringing to our resistor is 12 times 4, would be 48. Okay, so the idea being because we're delivering 4 thingies, coulombs per second, and each thingy, each coulomb carries 12 joules, the total power delivered to our resistor is just the product of I and delta V together. So we can write that out in a little equation, say P is equal to I times delta V in general. That's our general equation. And sorry about the tight board here a little bit, but you know, we're working with what we got. 12 joules per coulomb, 4 coulombs per second. So our example, that would be 48 watts. Okay, so I'm just kind of clearly mark, what was this all about? The really important thing is this thing, right? So we come to the conclusion that we can figure out the power that is delivered in a circuit if we know how much current's flowing and what kind of potential difference it is. Okay, so we'll get back to this on Monday. When I see you the next time, I'll record this. I'll finish the recording now and I will post it on YouTube if you want to look through this again. And I'm also going to send you a picture of the board.